may be considered as a series of hypothetical steps. Let's take a metal ion. So here we have cobalt 3 plus ion. The outermost electronic configuration of cobalt atom is 3d7 4s2, and the outer shell configuration of cobalt 3 plus ion is 3d6. Let's understand how we get that. The atomic number of cobalt is 27. The number of electrons present in cobalt 3 plus ion will be 27 minus 3, that is equal to 24 electrons. The outer shell configuration of cobalt atom is 3d7 4s2. We can clearly see that there are 2 electrons in the 4s orbital and then there are 7 electrons in the 3d orbital. Now if we have to remove 3 electrons in order to represent the outer shell configuration of cobalt 3 plus ion, 2 electrons are removed from the 4s orbital and 1 electron is removed from the 3d orbital. So we will have 3d6 as our outer shell configuration of cobalt 3 plus ion. Let's understand how to arrange these electrons. Here we have a representation. This is the 3d orbital of cobalt 3 plus, 4s, 4p and 4d orbitals. There are no electrons in the 4s, 4p or 4d orbitals in the cobalt 3 plus ion. We have only 6 electrons in the 3d orbital and that is our outermost orbital. And how do we arrange these 6 electrons? 1, 2, 3, 4, 5 and the 6th one is paired with the first electron here. So this is how the 6 electrons of cobalt 3 plus ion are arranged. If this ion wants to form a complex having 6 ligands, then 6 atomic orbitals are required in order to accommodate the lone pairs of electrons that these 6 ligands will be bringing. So we have 6 ligands here. That means we are dealing with 6 lone pairs of electrons. In order to accommodate these electrons, 6 atomic orbitals are required. So what happens here is the 4s orbital, the 4p orbitals and the 4d orbitals undergo hybridization to give sp3d2 orbitals. So how many orbitals are going to be involved over here in total in the process of hybridization? We have 1 s orbital, we have 3 p orbitals and we have 2 d orbitals. So that is equal to 6. These 6 orbitals hybridize and give this hybridized set of sp3d2 orbitals which are vacant. And these are the orbitals that will receive and accommodate the lone pairs of electrons that will be brought by the 6 ligands. The 6 lone pairs of electrons brought in by the 6 monodentate ligands will be arranged in the hybridized orbitals as follows. 1s orbital, 3p orbitals and 2d orbitals have hybridized to form the sp3d2 hybrid orbitals. So now we have 1, 2, 3, 4, 5, 6 hybrid orbitals that are going to accommodate the lone pairs brought in by the ligands. So let's consider these are our ligands L1, L2, L3, L4, L5 and L6. And assuming that these are monodentate ligands, that means each of them is going to donate only 1 lone pair of electrons. So the lone pair brought in by this ligand goes here, L2 ligand pair goes here, same for L3, L4, L5 and L6. So in this way, the vacant orbitals, which are degenerate orbitals, the meaning of degenerate orbitals is that all these orbitals have the same energy. So these hybridized orbitals which are degenerated nature, accommodate the lone pairs brought in by the monodentate ligands as follows. And this is how a coordinate covalent bond is formed, where one of them brings only the lone pair and the other one accommodates. So here the vacant sp3d2 orbital of cobalt 3 plus is accommodating the lone pair brought in by each of the ligands. The valence bond theory. This theory was mainly developed by Linnaeus Pauling. Let's understand the main features of this theory. Every metal ion, when it forms a complex compound, undergoes the formation of coordinate covalent bond. That means during the formation of a complex compound, we are going to witness the formation of a coordinate covalent bond. In here, we have seen that coordinate covalent bonds have been formed between the sp3d2 hybrid orbitals of the metal ion and the ligands. During this bond formation, the metal ion acts as an electron pair acceptor. For this, the metal ion provides vacant orbitals. In here, the metal ion has undergone hybridization and kept vacant orbitals ready in order to accept and accommodate the lone pairs of electrons. While the ligands were clearly acting as electron pair donors, the metal ion was accepting the electron pairs and was acting as electron pair acceptor. The number of vacant orbitals provided is equal to the coordination number of metal ion. Let's take an example. In the formation of the hexaamine ion 3 complex, Fe3 plus ion provides 6 vacant orbitals, which means the coordination number of ion in this case is 6. In the formation of the tetraamine copper 2 complex, Cu2 plus ion provides 4 vacant orbitals. That means the coordination number of Cu2 plus ion is 4. The metal provides vacant orbitals only after the process of hybridization, thus vacant hybrid orbitals are provided by the metal ion. The vacant hybrid orbitals were available only after the process of hybridization. Only after the 4s, 4p and 4d orbitals hybridized, only after that the vacant orbitals were available in order to accommodate the lone pairs of electrons brought in by the ligands. The vacant hybrid orbitals of metal ion get overlapped by orbitals of ligands containing lone pair of electrons. In the process of the coordinate covalent bond formation here, what is happening is that the vacant orbital of the metal ion is getting overlapped with the orbital of the ligand containing the lone pair of electrons. This vacant orbital and the orbital containing lone pair overlap is what is causing the formation of the coordinate covalent bond. The number of such overlappings is equal to the coordination number of the metal ion. In here, we have 6 such overlaps. 1, 2, 3, 4, 5, 6. So in this case, the coordination number of the metal ion is 6. The empty d orbitals involved in hybridization may be inner n-1 d orbitals or outer nd orbitals. Let's understand what is the meaning of inner n-1 d orbitals and outer nd orbitals. In case of the cobalt 3 plus ion here, the fourth shell is the outermost shell, that is the end shell. And the third shell is the penultimate shell, that is the shell before the outermost shell. So that becomes the n-1 shell. During the process of hybridization, the d orbitals of either the n shell or the n-1 shell could be a part of the hybridization. If the d orbitals of the n-1 shell are involved in hybridization, we call them the n-1d orbitals or the inner n-1d orbitals. If the d orbitals of the n shell are involved in hybridization, we call them the outer nd orbitals. These complexes are called as inner orbital complexes and outer orbital complexes respectively. It is applicable for the complexes having the coordination number 6. If the d orbitals of the n-1 shell, which are called the n-1d orbitals or the inner n-1d orbitals, if these d orbitals are involved in the hybridization process, then that complex is called an inner orbital complex. If the d orbitals of the outer shell, that is the n shell, are involved in the process of hybridization, then we call the complex as the outer orbital complex. If inner d orbitals are involved in hybridization, then it is through the pairing of unpaired electrons in the n-1d orbitals of metal ion. In this case, we can clearly see that the d orbitals of the n shell, that is, the nd orbitals or the outer nd orbitals, are involved in hybridization. But in cases where we see the d orbital of the n-1 shell involving in hybridization, we also get to witness something known as force pairing. Now, what happens in force pairing is that whatever are the unpaired electrons that we see here, they force pair themselves. That is, for example, these two electrons and these two electrons. So here we have 4 unpaired electrons. After force pairing, we are going to get 2 pairs of electrons, leaving 2 empty orbitals. That is the meaning of force pairing. So in cases where the d orbitals of the n-1 shell are involved in hybridization, we get to witness this force pairing phenomenon, which of course is not the case over here because we can clearly see the outer d orbitals involving in hybridization. So that's the meaning of when n-1d orbitals are involved in hybridization, then that is usually through the pairing of unpaired electrons. We have just understood what that means. Then such type of complexes will be diamagnetic or less paramagnetic and will be called as low spin complexes. This here is the electronic configuration of the cobalt 3+ ion. In this case, the 4d orbitals are called the outer d orbitals and the 3d orbitals are called the inner d orbitals. Let's imagine a situation where the 3d orbitals will be participating in hybridization. In such a case, whatever are the unpaired electrons in that d orbital start forming pairs. Let's understand how the electronic configuration would look like if the unpaired electrons over here form into pairs. This is how the arrangement of electrons would look like. We can see that these 3 orbitals are filled with pairs of electrons and these 2 orbitals are vacant, and these are the orbitals that will participate in hybridization. We can also observe now that there are no unpaired electrons and we have 3 pairs of electrons. An atom or ion that has all of its electrons paired exhibits less or nil magnetic character. If it exhibits nil magnetic character, it is called diamagnetic in nature. The complexes which are formed due to the hybridization of inner d orbitals are mostly going to be diamagnetic in nature, because during this hybridization process, the electrons that are present in the inner d orbitals tend to form into pairs, and mostly all of them end up pairing. Hence, there will be no electron left unpaired, and that leads to diamagnetic character. However, in cases where one electron is remaining unpaired, then that might lead to a little bit of paramagnetic nature. But most of the times we get to see diamagnetic complexes where n-1d orbitals are involved in hybridization. Now these complexes where the n-1d orbitals are involved in hybridization are also called the low spin complexes, because in the process of force pairing that is happening over here, the spin of electrons is getting reduced because of the process of pairing. Hence the name low spin complexes. So remember, more the number of unpaired electrons present, more is going to be the spin of that complex. And by the same logic, if less the number of unpaired electrons present, less is going to be the spin of that complex. Generally, outer orbital complexes have paramagnetic nature, and they are called as high spin complexes. The complexes that are formed due to the n-d orbitals involving in hybridization are called the outer orbital complexes. Now the reason why most of them are also paramagnetic in nature is they end up having one or more unpaired electrons, and when there is a presence of unpaired electrons, that leads to paramagnetic nature. And since the number of unpaired electrons is directly proportional to the spin, more the number of unpaired electrons, more is going to be the spin of that complex. These complexes are also called high spin complexes. So n-d orbitals lead to high spin complexes. That is, the participation of n-d orbitals in the hybridization process lead to the formation of high spin complexes, and most of them are paramagnetic in nature. Of course, we can definitely call a complex paramagnetic only if there is at least one unpaired electron. If there are no unpaired electrons, then we cannot call that complex a paramagnetic one.